Okay, so if you enjoyed the mental hoop jumping, as we called it last time, of kind of manipulating identities and moving them around and coming up with new expressions and things like that, you may enjoy 5.2 because it's on verifying trig identities. But again, if you've struggled with this at all, please come and see me. Please make sure you're asking plenty of questions, because these can be a little bit weird. So what we're going to do is we're going to verify identities in this section. And just as a reminder, what is an identity? It is a blank equation. What type of equation is it? It's a true equation. Okay, so an identity is a true equation. It's an equation where as long as the two sides are defined, you can plug the same number into both sides and the two sides equal each other. Okay, so one expression is just as good as the other expression. So this would be a silly example. $1 is equal to 4 quarters. Okay, those two things are equal. Okay, and if I were to put an x right here, and then I were to put an x right here, those two things would still be equal, and it wouldn't matter what I plugged in there. Okay, all right. So we're basically going to be showing that some equations are true, and this is some guidelines that the book has, and you'll notice that they're called guidelines. Last time when I had you write a few things down, like sometimes it's nice to work with the same trig function or the same angle and stuff like that, I said that's not a step-by-step list. It's not like you go through and do this, then this, then this, then this. Okay, and the same thing is true here when we're verifying identities. This isn't go through and do this, then go through and do this. It's keep all of these guidelines in mind as you're working through a problem. So the first guideline is this, and this is what the book has, and then I've got some other guidelines that I'll put down below. So work with one side of an equation at a time. So generally speaking, we're going to pick the more complicated side, and we're going to make it look like the simpler side. So we're going to pick that one complicated side, and we're going to try and make it look like the simple side. Now, there are books that say it's not correct to work on both sides, okay? And then there are other books that say it's okay to work on both sides, and you'll see what I mean when we get there. Generally speaking, it's best if you do all your work on one side. Pick the complicated side and make it look like the simple side. Look for opportunities to factor an expression, add fractions, square a binomial, create a monomial denominator, stuff like that. This is a bunch of algebra. A bunch of algebra, and then using some of those basic trig identities that we were talking about before. Look for opportunities to use those fundamental identities. So change things into sines and cosines. Okay? Like they said right here, sines and cosines pair up well. Okay? As do secants and tangents. Why do secants and tangents pair up well? Why would it be good to have everything in terms of secant and tangent, maybe? Remember those Pythagorean identities? Isn't it sine squared plus cosine squared equals 1? And isn't it 1 plus tangent squared, or tangent squared plus 1 equals secant squared? And then the same thing for secant and cotangent, or cosecant and cotangent. Okay? If the preceding guidelines do not help, try converting all terms into sines and cosines. I actually like this one before I like working with tangent and cotangent and secant and cosecant. Most people are better at working with sines and cosines. Okay? Oh, and I notice I've got a repeat here. Always try something. Even paths that lead to dead ends give you insight. So if you bark up the wrong tree or go down the wrong path for a little while, that's not necessarily the end of the world. At least that's something that didn't work. And it may end up that you can get one side to look almost like the other side, just flipped over, or maybe a plus or minus or something like that. And then you just make an adjustment on the steps you did. So there are going to be times where you try something and work for 3 or 4 minutes, and you figure out, oh, that doesn't work, I've got to start over. Okay, and generally speaking, that's what gets frustrating about these. Okay, so let me just add this, and I'll have to adjust these because I didn't realize this. Sometimes it's easier to work with sine and cosine. Okay? I like doing that, generally speaking. It's sometimes easier to work with the same trig function and the same angle. We're not going to have too many of them have different angles, but if you do run into that, we are going to learn some identities over the next week or so where we can change one angle into another and things like that. Okay? And then another thing that I've found helpful is look at the side you're not working on for hints about what to do. How many terms are there? Okay. What trig function is used? And things like that. So I've got, let's see, 1, 2, 3, 4, 5, 6. I've got 6 examples that we're going to take a look at. These are similar but not the same as the ones in the book. You've got the assignment for 5.2. I got that on the website, and I think I showed that to you last time. I didn't hand that out though, did I? Okay. I'll pull that up. In fact, I'll pull that up right now so we've got that. Okay. Here's 5.2. Let me read the numbers. You write them down. Ready? 2, 3, 4, 9, 11, 14, 21, 22, 32, 33, 35, 37, 48, 49, 78, and 79. Okay? And this is on the website, and I apologize. I probably should have run a copy of this for you. Okay, so we're sitting right here. We're going to do 5.2 today and tomorrow. We'll have a quiz on identities on Thursdays, and then on Thursday. Then we'll cover 5.3 and 5.4. We'll have a test a week from Friday. Okay, just on chapter 5. Okay, so again, these are similar to the ones in the textbook, not the same. You really want to see as many examples as you can so you get the hang of it. So let's take a look at this one right here. Again, generally speaking, we're going to work on the more complicated side. So which of these two sides is more complicated? The left side. Okay, this is much more complicated. Okay, now you'll notice that I've got 2 terms on the top and I've only got 1 term over here. Okay. Does any part of this look familiar? Is there anything that somebody would want to suggest? Maybe it's the right thing, maybe it's not the right thing, but we should at least try something. Cameron? The top said very well. The top is a mixed up Pythagorean theorem. So we're probably thinking of this. Sine squared x plus cosine squared x equals 1. So in order to do this, I could do a couple of different things. Okay, I kind of like making it look the same, so I'm going to do this. I'm going to move the cosine to the other side and the 1 over here. That's going to make sine squared x minus 1 equals cosine squared x. Is that okay? Negative cosine squared? Okay. Little mistake like that would make it so this wouldn't turn out to be negative. Okay, and then I can just make that substitution. Wherever there's a sine squared minus 1, I can put a negative cosine squared. So I've got negative cosine squared x over sine squared x. And what is this? Negative cotangent squared x. And I like circling that and kind of drawing an arrow and saying I'm done. Now, if you're going to do this right, I mentioned last week we probably ought to add something else. How did I go from this step, from this expression right here to this expression right here? It's a rationale, it's a reason. What reason would I give? Yeah. Right, Pythag for Pythagorean identity. How do we go from here to here? Quotient identity. Okay. Okay. So if I say Pythag and quotient, I mean Pythagorean identity and quotient identity, and I'm all set to go. Does that make sense? Everybody good there? Okay, watch. Okay, that is a perfectly good way of doing it, but if you were given this on a test, and let's say you got your test back, you and your neighbor both got it right, but your neighbor did this. Thought of the Pythagorean theorem, or the identity this way. And then wherever there's a sine squared, they wrote 1 minus cosine squared x minus 1 over sine squared x. 1 minus 1 is 0. Okay? And then they have negative cosine squared over sine squared. So then they wrote cotangent squared. And they said Pythagorean identity was the rationale or the reason for this, and quotient identity was the reason for that. They're done differently, but are they both correct? Absolutely. What's that? Oh, thanks for getting that today. It's Monday, right? Yeah, and we forgot the pledge too. Holy cow. It's horrible. Doing horrible today. Okay? Yeah. Any questions? Yeah.
So on that, when they're substituting, why wouldn't they put the 1 minus cosine squared on the bottom as well?
You could, but if you did that, then you'd end up. So here's Nathan's question. If we did this on the top, and we did it on the bottom, that would go away, and that would leave us with negative cosine squared x on the top and 1 minus cosine squared x on the bottom. Okay? And then are we any closer to where we need to be? Not really. It's kind of like, if you take a good look at it, it's this one flipped over with a different trig function. It's cosine squared rather than a sine squared. So the reason we only substitute it for this one right here, put it in place of that guy right there and not both the top and the bottom, is we know we're looking for a cotangent. A cotangent is a cosine over a sine. So that's what we're trying to get. That's why we leave the sine squared on the bottom. Okay? Again, take some getting used to. Are these the only two ways to do that problem? Absolutely not. We could do this and then work on that until we ended up with a negative cotangent squared. That would be fine. Okay? But that would be a much more roundabout way to do it. I think that the most straightforward way to do it is the way we did it first. This is probably second most straightforward, and then after that, there are probably dozens and dozens of ways to do it, but they're all fairly complicated. Okay? Any questions? Okay, let's take a look at this one right here. And then usually the question is, where do we start? And which side is more complicated? So on this problem, which side's more complicated, left or the right? Left. Okay? Now, when I set up here, look at the side you're working on for hints about what to do. How many terms do I have on this side? 2. And how many terms do I have right here? Only 1. So if I'm going to turn these 2 terms into 1 term, I better combine those together. I better put them together. All right? So if I'm going to combine those, what do I need to do here? Get a common denominator. So I need a denominator of, whoops, like that. Giving me trouble here, it's disappearing. Okay, so I need a, let's see, a secant x plus 1 here. And what do I need over here? I need a secant x minus 1. Now, this looks like it's going to be absolutely awful. One of the struggles is you've got to remember a lot of algebra when you're doing these. So if I were to multiply secant x plus 1 times secant x minus 1, if I multiply those together, what do I get? Yep. It's a difference of squares. Aren't those conjugates of each other? So I get secant squared x minus 1 in the denominator. And up here I have secant x plus 1. And then I have minus, and I'm going to put this in parentheses, minus secant x minus 1. Got a common denominator. When I multiply them together, I've got a secant squared x minus 1. This one was just secant x plus 1 times 1, so that's all it is right there. And then this negative is really important. We're subtracting all of this stuff. Now, if you want, you could get rid of the parentheses and write minus secant x. Hold on one second. Maybe we've overwhelmed the... There we go. Okay. So my question for you is that right? What's wrong? Yeah, you've got to distribute that negative through to both of these, so it's going to be a minus secant, and then if I do a negative times a negative, I end up with a positive. Okay? What goes away on the top? Okay, so secant x and secant x. Okay, we probably ought to add a rationale here. Okay, we got a common denominator. Okay, and then I'm going to cross those two off. Good. So this gives me a 2 on the top and a secant squared x minus 1 on the bottom. Any ideas on what to do next? Lynn? Okay, so we're going to use a Pythagorean identity. And the identity we're going to use is, remember, secant and tangent go together. So it's tangent squared x plus 1 equals secant squared x. Or if I just move this over to the other side, that means that tangent squared x is equal to secant squared x minus 1. So wherever there's a secant squared x, what can I put? I can put tangent squared. So common denominator, maybe write simplify here, and then Pythagorean identity. And then what's next? Are we there? What's 1 over tangent? Yeah, it's cotangent, right? So this would be 2 cotangent squared x. There's our answer. Okay, what's the reason for this last one? What's it called again? Reciprocal. So reciprocal identity. Okay? All right, any questions there? Take a little getting used to. Let's take a look at this next one. Okay, now, for some reason, most books set it up so the left side is the most complicated one. It's been that way on the first two, and this one, the left side is the most complicated again. Okay, so let's go ahead and try and work this. If I were going to do this, what would I probably want to do first? What's that? We could do a Pythagorean identity. Okay, we could do a Pythagorean identity. Well, we've got a couple choices there, don't we? Got a couple choices. Do you want to get rid of the cotangent, or do you want to get rid of the sine? Get rid of the sine? Okay. So let's see. I'd want to be using this one, or some form of this one. Okay, the fundamental trig identity. Okay, that's the one we start all of those with. And again, if you can see how to make this 1 minus sine squared, go right ahead. Wouldn't it be cosine squared x equals 1 minus sine squared x? Is that okay? I've got one term on this side, but it's got 2 factors, and each factor has 2 terms in it. So by doing this, I'm going to be able to put a cosine squared here. And the rationale or the reason for that is Pythagorean identity. What now? We want to make this side into just a cotangent squared. I've got all this extra stuff. I've got a 1 and I've also got a cosine squared. Can we change this to cosecant squared? Okay. Well, let's see. If this was the original one, then remember, if I want to make a cosecant, I'd have to divide everything by sine squared. So if I divide this by sine squared, I get 1. If I divide that by sine squared, I get cotangent squared. And then over on this side, I have cosecant squared. Is that good? So I'm going to replace this with a plain old cosecant squared. So this is cosecant squared x times cosine squared x. And again, the rationale for that is Pythagorean. Now, Brandon may have a good idea how to do this problem, but if Brandon's idea was the wrong thing to do and it got us further away from the answer, we're probably going to be able to figure that out fairly quickly. Some of you may know what Brandon's after and what to do next, and some of you might still be looking at this going, I don't know what's going on here. I'm not sure what to do next. Okay? We're on the right track here. In fact, we're really close to being done. I need to use one more identity, and then it should be crystal clear to everybody how to finish this off. So can somebody tell me what we're going to do next? Lynn? Change cosecant squared to 1 over sine squared. So if I make that change, so this is 1 over sine squared x times cosine squared x. And again, the reason for that is these are reciprocals. That's a reciprocal identity. Once I do that, then I have cosine squared x over sine squared x. Okay, and if you had to write down a reason for that, we're basically just simplifying fractions. Okay, we're multiplying them. Good? You could just write simplify. And then the last thing we do is we say, well, this is cotangent squared x. There's the answer, and the reason for that is quotient identity. Any questions? Takes quite a bit of practice to get good at these. Okay, now look at this one. Yeah.
Could you break the right side up into two fractions and then change them to cosine?
Okay, so here's the idea. Just watch, listen, don't write anything down. The idea would be to break this into that minus that, and then write everything in terms of sines and cosines. Is that what you're thinking? Yeah. Okay. Can you do this? I see some shaking heads, yes. And I see some shaking heads, no. Let's stop and think about this. If I were to write 1 over 4 plus 3, is that the same as 1/4 plus 1/3? Nope. Okay. I can't break fractions apart that way. I can't take the numerator or the denominator and break it over the numerator. Okay. I can do this. Okay. If this were upside down, if this had been 3 plus 4 over 7, for example, I can do 3/7 plus 4/7. That would be the same thing. So I can break the numerator up over the denominator. I can't take the denominator and break it up over the numerator. Does that make sense? Okay, so that one's not going to work. and I've got one term here, and I need to turn it into two terms over there. Okay, there are several different ways to do this problem. Does anyone want to make a suggestion? Because I'm going to show you something that you probably haven't seen before, but you'll want to put this in your bag of tricks, your toolbox, because this type of thing comes up a whole lot. Okay, I'm going to put this in parentheses, and I'm going to multiply by, nope, its conjugate. I'm going to multiply by its conjugate. It's kind of like rationalizing the denominator. That conjugate idea, that difference of squares idea, comes up all the time. It's amazing where it crops up. So here's what's going to happen. I really don't have that many trig functions or trig identities to deal with here, and they're all pretty nasty. But if I do this, watch what happens. So I'm going to multiply by the secant of u plus the tangent of u. Secant of u plus the tangent of u. Take a good look at that. Notice that if I ignored the denominator, if I covered up the denominator, doesn't it look exactly like it's supposed to there? So that's kind of promising. Now look what happens here. Okay, now the step that I'm doing here, we'll come up with a rationalization for this in just a second, but the numerator is going to be secant of u plus the tangent of u, which looks fabulous. Write down what the denominator is. It's a conjugate, so it's going to be a difference of squares. It's going to be secant squared u minus tangent squared u. And again, the rationale for going from here to here, is we could say mult by conjugate. What we did is we just multiplied by a 1. We could say we're making squared trig functions, but we're doing a legal algebraic move in order to get that into something that we can now manipulate. Does any part of this look familiar? Trig function squared, right? Might be a Pythagorean identity. It is, okay? So if you think of the original one, and I need a tangent, that's the way I like to think of it. If I divide everything by cosine, that would be tangent squared x. That's going to be 1, and that's going to be secant squared x. So if I move this over here, and that to the other side, let's see. Yep. Okay, so here's what I need to do. I need a positive secant, and I need a negative tangent squared. So I'm going to move this to the other side. So 1 is going to be equal to secant squared x minus tangent squared x. So wherever this appears, wherever I have a secant squared minus a tangent squared, I can put that over a 1. And the rationale for that, Pythagorean. And then I've just got secant of u plus tangent of u. And now I've made this side look like that side. Okay, please don't lose track of that. Okay, I can kind of rationalize that or get that into a form where I might have some other identities that I can use, some of those Pythagorean identities, if I can get each one of those to be squared. And the way I can get each one of those to be squared is by multiplying by its conjugate, multiplying by a difference of squares. Okay, very nifty trick used all the time. Is that the only way to do this problem? It's not. If I were to do this problem, what I would probably do is I might even take this and write it in terms of sines and cosines, or maybe write this side in terms of sines and cosines and see if I could make it look like that. Okay, but, I think that would get you there. Not as slick as this, so that's why that's a good trick to use. Okay, any questions? Okay, would you try that one? Give you a couple minutes. You want to make one side look like the other side. Okay, and let me stop you right there. Raise your hand if you're working on the left side. Raise your hand if you're working on the left side. Okay? Raise your hand if you're working on the right side. Okay? Raise your hand if you have no clue what to do. Okay, all right, that's good. Okay, Peyton's working on the left side, and that's fine. Okay, stop and think about this. Are we usually better at, so this is one term, are we usually better at taking two different terms and simplifying them to be one term? Or are we usually better at taking one term and breaking it apart into a couple different terms? Usually we're better at taking terms and putting them together. So I think this side is the more complicated one, and I think it would be easier to make it look like that one. Okay? Now that's just me. And if everybody's working on this side except for Peyton, we'll go ahead and do it that way, and then we'll see what Peyton does. So pressure's on, Peyton. What do you think we ought to do first here? We're going to work on this side. So Brandon changed this into 1 over sine of t minus sine of t. I've got two terms. I used a reciprocal identity in order to do that. This looks good because I've got the same trig function. You may be ahead, but I'll give you 30 seconds or so to think about this. This looks pretty darn good to me. I like this idea. This problem is going to illustrate another common technique. Who can tell us what to do next? What do we do, Tammy? Common denominator. So the next thing we're going to do is we're going to get a common denominator. So the way we're going to do that is I need a sign down here in order to combine those. So I'm going to multiply the top and bottom by sine t. So that's going to give me sine of t in the denominator, and that's going to give me 1 minus sine squared t in the numerator. Here's what I've got. I've got one term over here. I've got one term here, and I've got one term over there. So that's good news. At least we're in the one term category. Okay? And then we look at this, and my gosh, part of this looks familiar. What's that? What's the numerator there? Part of the Pythagorean theorem, or Pythagorean identity, right? And again, if you visualize this, I write this on the board a lot, but I'm hoping that you just visualize this. If I move the sine squared to the other side, I have 1 minus sine squared, and 1 minus sine squared is cosine squared. So I'm going to write cosine squared t over sine t. And I did that by way of a Pythagorean identity. Now, I am nearly there. I'm almost there. I can make this look like that, but I have to do something that we don't do very often. Remember, we're normally used to simplifying things, writing them as simply and as compact as we possibly can. So if I write a cosine squared, that's the easiest way to write a longer expression. Cameron, what do we do? Split it up. We're going to write this as cosine of t times cosine of t over sine of t. So we could write meaning of square. That's what it means when we square. That's what that exponent means. And then again, something that we don't normally do. Break that up. Now, do I need to write cosine t over sine t and cosine t over sine t? Do I need to write it twice? That's wrong, isn't it? Okay? This multiplication problem should represent that fraction, right? And if I were to multiply the numerators, I get cosine times cosine, which would be cosine squared. On the bottom, I'd get a sine squared. So I only need this. So notice how there's a cosine and a cosine on the top and just one sign on the bottom. And what is cosine t over sine t? Cotangent t times cosine of t. And we could say quotient identity, property of fraction multiplication. Okay, any questions? Okay, we'll do one more and then I'll give you time to work on your assignments. Everybody got that one written down? Okay. Okay, look at that last one then. Which one's more complicated? Okay, I hear, anybody want to advocate for the right? Is the right more complicated? Okay, why is the left more complicated? What makes it more complicated? Okay, there's more than one trig function, I'll take that. Also, it's written in terms of cotangent and cosecant, which are certainly not our favorite. Sine and cosine are really easy to work with. Tangent, cotangent, secant, cosecant, those are a little more complicated. So we probably ought to change this into sines. And there's one term over on this side and one term over there, so that wouldn't help. But I do definitely think that that side is much more complicated. Any ideas on what we ought to do first? Okay, we could use a Pythagorean identity on this. So that would be 1 plus cotangent squared x equals cosecant squared x, right? So if I'm going to replace a cotangent, I'm going to move that over to the other side. So I'm going to write a cosecant squared, a theta, minus 1 over 1 plus cosecant theta. And we did that by way of a Pythagorean identity. We've eliminated one complication, at least it's now in terms of the same trig function. Take a good look. Take a good look. We're really not that far away from having the right answer. It's just that we probably haven't seen something like this done before. So your hint is, we've done this on this paper. We did this in class today, but we did this in reverse. What is it, Tammy? Very good. Take a look at this. This is the nice thing about Pythagorean identities. They are a difference of squares, most of them, or they can be arranged so that you've got a difference of squares. You can have a perfect square minus a perfect square. So if I were to factor this, here's what I'd get. I'd get cosecant of theta minus 1, cosecant of theta plus 1 over 1 plus cosecant theta. Now, if we take a good look at that, factor difference of squares. If we take a good look at that, how is that helpful? Yeah, this factor, even though this is a 1 plus cosecant, and this is a cosecant plus 1, the commutative property of addition, we can just move those around, we can cancel those off. So we're going to say cancel common factors. And then I've got this. I've got cosecant theta minus 1. That's where I am. And I need to make it look like this. So here's where I am. I need to make it look like that. I've got two terms here. I've got one term here. I've got division in this one. I don't have any division in this one. This one is cosecant. This one is sine. So I don't want anybody to say anything out loud. I think everybody in here should be able to figure out what to do. What am I going to do to this one to make it look like that one? Don't say anything, just write it down. Think it in your head. And then I'm going to ask Logan, what are we going to do? Just go ahead and just times by sign? If we just times by sign, we'd have to multiply the top and the bottom by sign. I suppose we could do that. Okay. We couldn't just multiply by one sign. We'd have to multiply sign over sign. Okay. That could get us closer. Or is there an easier way to do it? Okay. Okay. Yep. So right, this is 1 over sine of theta minus 1. And then get a common denominator. So I'd need a sine theta, and I'd need a sine theta. So this gives me 1 minus sine theta over sine. And then it's the same. Yeah.
This is what I did. Could you now work with the 1 minus sine or whatever, break that up into...
Yep. Hang on 1 second. Hang on 1 second. Okay, so I'm going to change colors. Let's go back to what Logan suggested. If we just multiplied by sine, that completely changes the value of the expression. But if I multiply by sine theta over sine theta, I'm multiplying by a 1, right? Is that okay? And if I do that, watch what happens. So if I distribute that through, here's what I get. I get a cosecant theta, sine theta, and then minus sine theta over sine theta. What's cosecant? One over sine. So I could cancel this with this. That would give me a 1 over sine theta minus sine theta over sine theta. Isn't that where we are right here? Couldn't I combine them together and get this? So would that get us there? Yeah, maybe a little bit more roundabout way, but that would be just fine. Okay, here's Brandon's question, and let me highlight where we were. We were right here, right? Okay, we were right here, and he was looking at the two of those things. So Brandon's idea is to do this. What's your idea, Brandon?
You work with the 1 minus sine theta over sine theta, and you put 1 over sine theta minus sine theta over sine theta. And sine theta over sine theta becomes a 1, so it's 1 over sine theta minus 1. And then the 1 over sine theta becomes cosecant theta.
And then this side, in one step, we've made this side look like this side. Okay? That's an example of working on both sides. Is that the best way to do a problem? Generally not. Are there some teachers, some textbooks that don't like that? Absolutely. Is there anything inherently wrong with it, though? There's not. Okay? What's nice is if we work on one side and we can just say, okay, step, 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 you can see exactly what happened here. What we did on this one is we did some work on this one, did some work on this one, and then said, you know what, these two things are equal to each other. That's okay, it's just not the best way to do it. Yeah. Simplify like from the beginning or from right here?
From the beginning, just the right side, isn't it?
Simplify this into cotangent? Yeah. Let's look at it a little more closely. You can work on both sides, and the thing that gets frustrating for most people is there are probably dozens of ways to do each problem, okay? As long as you can follow your steps, as long as your rationale is there, you're okay. Go ahead and get started on the assignment. Tomorrow we'll just do questions and make sure everybody knows how to do these, okay? Hang on 1 sec.